Greetings of the day. I'm Dr. K. Raghuram Mohan Reddy. The course name is Unconventional Machining Process. Today's topic is applications of laser beam machining. Okay. So at the end of this session, student will be able to understand the applications of laser beam machining. Okay. Right. So as part of just brief collection of the things from non-traditional machining process. So under this non-traditional machining process, we have three broad categories: mechanical, thermal, chemical and electrochemical. Under mechanical, ultrasonic machining, water jet machining, abrasive water jet machining, ice jet machining. In chemical and electrochemical, chemical milling, plasma chemical milling, electrochemical. Under thermal, electro discharge machining, electron beam machining, laser beam machining, ion beam machining, plasma beam machining. Today we are focusing on laser beam machining. Under that we are discussing the applications of laser beam machining. So in these areas we have laser beam machining applications. The first one is drilling, cutting and grooving, texturing and structuring, dressing of grinding wheels, milling, fine cutting and drilling, marking of computer keyboard, trimming of electronic components, controlled fracturing, dynamic balancing of gyro components, scribing, micro machining, laser assisted electro discharge machining. So these are the various applications of laser beam machining. Let us discuss one by one. The first one is drilling. Let us discuss the brief about this drilling of laser beam machining. Right. We have already discussed the various metals, materials associated to different manufacturing processes and different applications. Okay. So one of the predominant material is composite material. Right. Composite materials and some exotic alloys have been widely used in the fabrication of both structural and non-structural members, the airframes and engines of aircrafts. Okay. So here we need to have lightweight and high strength material for airframes and engines of aircrafts. So for this purpose we have to use composite materials and exotic alloys. Okay. Right. Second one is super alloys. Super alloys are used frequently for the fabrication of aero engine gas path components such as blades, guide vanes, afterburners and castings where a temperature of 2000 degrees centigrade can be reached. Okay. So usually the turbine blades of the aeros, the temperature would be very high, where the general materials may not be withstand that high temperature. So we have to use super alloys for the fabrication of aero engine gas path components. Okay. Right. So usually these superalloys are very high strength and high hardness. So it is very difficult to cut or machine or drill. Okay, with the all traditional machining process, but here we are using laser beam machining. Right. Advanced ceramics and titanium alloys. Third one, advanced ceramics and titanium alloys are being developed and used. Okay, such materials need advanced technologies in their fabrication and processing. See here, titanium alloys cannot be machined with the traditional machining process. Okay, with single point cutting tool of traditional machining process, we cannot machine the titanium alloy. Okay, even advanced ceramics. Okay, like tungsten carbides, etc. Okay, right. Conventional drilling and punching are found to be insufficient because of the material toughness. Already we have discussed the titanium alloy has high strength and low weight when compared to other materials, and it is too tough and too hard to machine with conventional process. Okay, so conventional drilling is not suitable for the advanced ceramics and titanium alloys. Okay, right. Next, other non-conventional process are there along with the laser beam machining are electrochemical machining. Okay, in the first slide itself we have briefed all the mechanical, thermal, and what is that? This one, chemical and electrochemical. Okay, so in this slide we have discussed all these non-traditional machining process. So, however, let me go through once with the present electrochemical and electrochemical drilling, EDM, ultrasonic machining, water jet machining, and abrasive water jet machining. Okay, so suffer from the high cost of tools and long lead times. So though we have all these process, non-conventional process, here the thing is that high cost of tools and long lead times. So it takes much time for the machining process. So here the material removal rate would be very low, and it is indirectly led to high cost. Okay. However, the tool cost is also very high with these processes. Okay, right. The capability of laser beam machining to produce fine holes at high machining speeds compared to the machining process is reviewed by Snoyes et al. During 1986. Okay, so during 1986, scientist Snoyes and et al. Found that laser beam machining is producing fine holes at high machining speeds compared to the other machining process. Okay, since the 1970s, laser drilling has proven to be an efficient drilling tool in terms of cost, quality, and reliability for large-scale production applications. Okay, so since 1970s, laser beam machining is cost-effective and quality of the laser beam machining is also proved, and reliability also good with the laser beam machining process. Okay, right. Laser drilling is performed by the following three methods. Okay, so laser drilling is performing with the following three methods. First one is direct drilling, that is percussion. Drill and ream, that is the second one. Third one, tree panning. Okay, let us discuss these three in detail. Okay, what is direct drilling, what is drill and ream, what is tree panning. Okay, of course, these are similar to our conventional process. Right. Now let us see direct drilling, that is percussion. Okay, right. So here produces the required hole size by the application of one or more focused laser pulses. Okay, the hole size is determined by the input power and the focusing adjustments. Okay, the hole size is determined by the input power and the focusing adjustments. While most holes are drilled with a single laser pulse of high energy, it is more efficient to drill deep holes with multiple pulses of low energy. Okay, so here the comparison between single laser pulse and multiple laser pulses. Okay, towards deep holes. Okay, right. Let me repeat. Most holes are drilled with a single laser pulse of high energy, but it is more efficient to drill deep holes with multiple pulses of low energy. Okay, so if it is a normal hole, then we can go with single laser pulse of high energy, but the hole is to be deep drill, then we have to go with multiple pulses of low energy. Okay, right. Under such circumstances, Yo et al. During 1994 and Tam et al. During 1990 produced better defined holes. Okay, so simply making holes is not a simple one. Here we have to focus on selecting whether it is suitable with single laser pulse of high energy or multiple pulses of low energy. Okay, so here the criteria is it should be cost effective and the quality hole. Okay, right. Consists, next one, drill and ream, second one. Okay, here it consists of drilling a pilot hole and then changing the laser parameters by increasing the spot size to open out the hole to the required diameter. Okay, so first of all we have to make a pilot hole. Okay, first we have to make a pilot hole and then changing the laser parameters by increasing the spot size to open out the hole to the required diameter. Okay, so that is nothing but the reaming. Okay, an alternative way introduced by Allen and Hong during 1997 is to drill a pilot hole using a laser beam and then apply EDM to obtain the true size. So here electrode discharge machining we have to adopt for the true size of the hole. Okay, right. Next, third one, tree panning. Used for large holes by either moving the part or rotating the laser beam system of delivery or lens. Okay, large holes by either moving the part or workpiece or rotating the laser beam system of delivery or lens. So either we have to rotate the workpiece or we have to rotate the laser beam. Okay, so we have to rotate the laser beam or we have to rotate the workpiece in order to have large holes. Okay, so because of low energy of each pulse, the recent layer and out of cylindricity are reduced. Okay, so because of the low energy of each pulse, the recast layer and out of cylindricity are reduced. The process, however, provides easier control of the hole size by rotating the diameter of the beam. Okay, right. Next, hole quality characteristics. So these are the hole quality characteristics. The first one is diameter and depth. Okay, how much diameter of hole that we have to produce and how much depth. So this is the depth, this is the diameter. Okay, diameter and depth. Next, taper and barreling. Second one is taper and barreling. Next, recast layer and micro cracking. Next, entrance angle. Next, drilling time. Okay, these 5 are the quality parameters of the hole. Okay, right. First one, diameter and depth. Okay, so here I have just exaggerated the hole size like this. Okay, but the hole diameter would be very less with the laser beam machining. Okay, right. Using laser beam machining, it is economically effective to drill holes up to 1.5 mm. Already I told you, here I have exaggerated this diameter, but the hole diameter is up to 1.5 mm only in diameter. For large diameters, the trepanning method is recommended. Okay, if we need more than the diameter hole, then we have to go with the trepanning method. Okay, right. The geometrical characteristics of laser drilled holes are described in terms of their aspect ratio, that is depth to diameter ratio at midspan of the hole. Okay, so here depth to diameter ratio, that is nothing but depth of hole by diameter of hole, that is aspect ratio. Okay, so the geometrical characteristics of laser drilled holes are described in terms of their aspect ratio, that is depth to diameter ratio at midspan of the hole. Okay, so here, right, the aspect ratio depends on the optical characteristics of the beam and the optical and thermal properties of the material. Okay, one is workpiece material, the other one is laser beam. Okay, the aspect ratio depends on the optical characteristics of the beam and on the optical and thermal properties of the material. Okay, so beam is having only optical characteristics and material will have both optical and thermal properties. Okay, so in deep hole drilling of 0.25 to 1 mm in diameter, typical aspect ratios of more than 10:1 have been reported by Yu et al. During 1994. So in the Yu et al. Research, it is clear that in deep hole drilling of 0.25 to 1 mm diameter, typical aspect ratios of more than 10:1. Okay, 10:1 means what? Depth to diameter ratio. See here, aspect ratio is depth to diameter ratio. Okay, so if the depth is 10 times and the diameter should be 1 time. Okay, an aspect ratio of 50:1 and the drilling tolerance of plus or minus 5 to 20% of diameter has been reported in the Machining Data Handbook in the 1997. So here from the Machining Data Handbook during 1997, the following figures have been reported for aspect ratio 50:1, that is nothing but a drilling tolerance of plus or minus 5 to 20% of the diameter has been considered. Right. Next, taper and barreling. Okay. Right. The degree of taper that ranges from 5 to 20% of the hole diameter decreases with an increase in the hole depth. Okay, so here the relation between hole diameter and hole depth, okay, towards the hole taperness. The degree of taper that ranges from 5 to 20% of the hole diameter decreases with an increase in the hole depth. Okay, when hole depth increases, what will happen? 5 to 20% of the hole diameter decreases. Okay, right. The taper depends on the pulse duration and the energy. Okay, the taper depends on the pulse duration and energy, the number of pulses and design of the optical system. Okay, so here taperness is depending on pulse duration, that is pulse time, and its energy and number of pulses and the design of the optical system. Okay, so these four influences the taperness of the hole. In general, shorter the pulse duration, the greater will be the taper. Okay, the short pulse duration will lead to greater the taperness. Okay, right. The scientific declaration, according to Yu et al. During 1994, barreling formed by the ejection of material from the local sites of the cavity can be reduced by decreasing the pressure of the assist gas. Okay, so it is a notable research towards the drilling. Right. Next one, recast layer and micro cracking. What is this one? Recast layer and micro cracking. Selecting a low power density that effectively expels molten and vaporized material from the machining zone can reduce the recast layer. Okay, selecting a low power density that effectively expels molten and vaporized material from the machining zone can reduce the recast layer. Otherwise, the recast layer will increase. Okay. Next, using a short pulse duration and low repetition rate to minimize heating in the surrounding material can reduce micro cracking. Okay, so here micro cracking should be reduced and eliminated. Otherwise, it affects the workpiece material in a longer time, even after the sophisticated laser beam machining. Okay, so here using a short pulse duration and low repetition rate to minimize the heating in the surrounding material. That means heat affected zone. Okay, so that it should be minimized. Okay, so it will reduce the micro cracking. Generally, the smaller depth of the altered layer associated with high cutting rates is an advantage of laser beam machining. Okay, so here micro cracking should be minimized and recast layer should be minimized. So in order to reduce the recast layer, what has been done? Selecting a low power density that effectively expels molten and vaporized material from the machining zone. Okay, so here selecting low power density and the using short pulse duration and a low repetition rate. Okay, so low repetition rate and short pulse duration are causing reduction of this micro cracking. So these two are very much important. Next, entrance angle. The laser beam is capable of drilling holes with an entrance angle that varies from 10 degrees up to normal incidence at 90 degrees with acceptable hole characteristics. Okay, so here the entrance angle is in the range 10 to 90 degrees. As the entrance angle with respect to the surface becomes smaller, the effective surface power density is reduced. Okay, as the entrance angle with respect to the surface becomes smaller, the effective surface power density is reduced. Under such circumstances, it is necessary to increase the power of laser or improve the quality of the beam. Okay, either we have to increase the power of the laser or improve the quality of the beam. Okay, right. In order to have the entrance angle in between 10 to 90 degrees and the effective surface power density to be reduced. Right. Next one, drilling time. Deep hole drilling up to 17 mm. Okay, so up to 17 mm depth can be accomplished by operating the laser beam in the rapid pulsed mode so that the total time is proportional to the amount of energy delivered per pulse. Okay, so here the economical aspect is one, the other side is how much depth that it can drill. Okay, so in deep hole drilling up to 17 mm can be accomplished by operating the laser beam in the rapid pulse mode so that the total time is proportional to the amount of energy delivered per pulse. So here drilling time is an important parameter for the economy of the operation, and at the same time how much depth that it can drill. Again, you et al. Found that the holes with similar aspect ratio can be drilled in a machining time, that is an aspect ratio of 20:1 is required 7 seconds. Okay, so aspect ratio of 20:1 requires 7 seconds. Okay, when it is having similar machining time. Right, now let us see the laser drilling capabilities. Okay, so the table represents the laser drilling capabilities. Okay, a diameter 0.005 to 1.27 mm larger in trepanning, depth 1.7 mm, angle 15 to 90 degrees, taper 5 to 20% hole diameter, depth to diameter ratio 50:1, drilling depth trepan 6.4 mm, tolerances plus or minus 5 to 20% diameter, minimum corner radius 0.25 mm. So these are the laser drilling capabilities. Okay, so these are the references to this topic. So with this, it is concluding for this presentation. Thank you very much. So in the next presentation, we extend the other applications. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.